In this video, we shall look at the second component of the Faster RCNN pipeline, namely the detector, in more detail. In my first video on Faster RCNN, I gave a very brief overview of the entire algorithm. I had mentioned that this is a two-step process where in step 1, we identify several region proposals in the image where there is a possibility of an object. Then the detector in step 2 tries to classify the object contained inside the region proposals and also fine-tune or refine the region proposals. Regarding step 1, I have already made an in-depth video on my channel. You can check out that video. I have added the video link in the description of this video. In this video, we shall focus on step 2, which is the detector, and study it in more detail. So let's begin. The outline of this video is as shown here. We will first look at the block diagram, then we will look at the network architecture, then the loss functions, the training, and finally the testing. Well, if you have watched my previous videos, this slide may be a little repetition, but let's quickly go through it again to get the context. We have seen that an input image is first passed through several convolution layers, which gives us feature maps, which are then used by the region proposal network, which outputs several regions of interest. These feature maps and the region proposals are then given to the detector. Inside the detector, each proposal is mapped onto the feature maps to extract features, which are then passed through ROI pooling layer to get fixed size features. These features corresponding to a particular region proposal are then given to the classifier and the regressor. The classifier predicts the class of the object contained inside the region proposal, and the regressor refines the bounding box parameters of that region proposal, which gives us the final result as shown on the left. Let us now try to understand the network architecture. It basically uses a pre-trained BGG16 network as shown here as the main backbone and breaks this network into parts and makes some interesting modifications. Let's see this in more detail. First, it uses all the layers up to the final max pool layer as highlighted in the red box here for extracting features. Precisely, I am referring to this part shown here, which produces the feature maps, on which each proposal is then mapped to extract features. Let us take it for now that we compulsorily need fixed size features for each region proposal, the reason I shall discuss shortly. But since each region proposal is of variable size, we obtain variable size features. The ROI pooling layer helps us to obtain fixed size features. Let us see now how this is done with the help of an example. Let us assume that we have a region proposal of size 12 cross 12 and there are C channels in the feature map. Now let's also assume that for every region proposal, we want to obtain features of fixed size 3 cross 3 cross C. ROI max pooling works by dividing the 12 cross 12 ROI window into a 3 cross 3 grid of sub-windows as shown here. It then applies max pooling in each sub-window, that is, it keeps only the maximum value in each sub-window to obtain the output feature of size 3 cross 3 cross C. Next, let us now try to understand the architecture of the classifier and regressor, which uses these fixed size features. For that, let's come back to this BGG16 network. We use these fully connected layers highlighted in red both for the classifier and regressor, but with a slight change. That is, in the classifier, we replace this last fully connected and softmax layer, which was trained for 1000 ImageNet classes, with a new fully connected and softmax layer containing k+1 nodes. And in the regressor, we replace it with a new fully connected and softmax layer containing 4k number of nodes, where k is the number of classes with which we want to train this detector. That is, for each region proposal, classifier outputs probability distribution over k object classes and the regressor outputs bounding box regression offsets for each of the k object classes. That's it. This is the architecture of the Fast RCNN detector. Only the newly added fully connected layers are trained from scratch, while all the other layers are just fine-tuned. Next, let's understand loss functions. There's one thing we need to understand first before going to the loss functions, and that is the ground truth. So let us say we have this image, and these are the region proposals produced by the region proposal network. We have seen earlier that each region proposal are one of the inputs to the Fast RCNN detector, where it tries to predict the class of the object contained inside the region proposal and also fine-tune the bounding box parameters of the region proposal. But to do that, we need to have the corresponding ground truth for each of these region proposals. But the fact is, we only have final ground truth bounding boxes and the object class labels as shown here. To obtain the ground truths for each of these region proposals, we proceed as follows. Let's consider these two region proposals. Let's overlay the final ground truths for better visualization. Now let's zoom into it a little. We first calculate intersection over union of each region proposal with all the final ground truth bounding boxes. For example, let's take this region proposal marked with the arrow. We can see that its IOU with the green box will be much less than 0.5 since the numerator will be very small compared to the denominator during the IOU calculation. We assign the ground truth object class label as 0 for such region proposals, where 0 represents background or no object class. And we do not assign any bounding box regression targets. But for this second region proposal, we can clearly see that the IOU with the green box is more than 0.5, and thus we assign the ground truth object class label as person and the ground truth bounding box regression targets as shown here, where x star, y star, w star, and h star represents center coordinates and width and height respectively of the green box, and similarly x, y, w, h corresponds to that of the white box. Now, having defined the ground truth object class label and the regression targets for each of the region proposals, let's now go to the loss functions one by one. First, let's define the loss function for the classifier. This is very simple. We just define the usual log loss or cross entropy loss for k-class classification. The equation is as shown here, where p is the predicted probability distribution over k classes including the background, and pu is the predicted probability of ground truth object class u. Whereas for the regressor, we use the same smooth L1 loss function as we studied in region proposal network. This is basically a mixture of L1 and L2 loss. The equation is as shown here. Here u is the ground truth object class and v represents the ground truth regression parameters which we just defined, and tu represents the predicted regression parameters for the object class u. Having defined the ground truths and the loss functions, the Fast RCNN detector can be trained end-to-end by backpropagation and stochastic gradient descent. Each training mini-batch is constructed from 2 images, and we sample 64 region proposals from each image, where 25% of the proposals have IOU overlap with a ground truth bounding box of at least 0.5, whereas the remaining proposals have a maximum IOU in the interval 0.1 to 0.5. There are many more aspects with regards to training which I suggest you to look into the Fast RCNN paper. I have added the link to the paper in the video description. Once it is trained, for each of the region proposal, the Fast RCNN detector outputs probability distribution over k classes including background and the regression offsets for each of the k classes. We assign the probability of each class as the detection confidence to the corresponding regression offsets. That is, if there are n region proposals, we obtain the outputs as shown here. Each row here corresponds to the bounding box outputs for a particular class. Next, we apply non-maximum suppression algorithm for each class to suppress redundant outputs, which shortlists few candidates as shown here. We can then obtain the x, y, w, and h of the output bounding box using inverse of this equation, which finally gives us our final output. So this comes to the end of this video. To summarize, in total, I made 3 videos on this faster RCNN based object detection algorithm, where in the first video on faster RCNN, I gave an overview of the entire pipeline and discussed the two main components, and then in the next video I discussed the first component, which is the region proposal network, in some detail. And in this video we looked at the second component, which is the detector part. So if you have not checked out these other two videos, I highly suggest you to have a look at it. I have given the video links in the description. And finally, these are the references. So in total, we looked at 3 papers as shown here. So that's it. See you soon in the next video. Thank you very much for watching this video.